A transit of Venus across the Sun takes place when the planet Venus passes directly between the Sun and a superior planet, becoming visible against the solar disk. During a transit, Venus can be seen from Earth as a small black disk moving across the face of the Sun. The duration of such transits is usually measured in hours. A transit is similar to a solar eclipse by the Moon. While the diameter of Venus is more than 3 times that of the Moon, Venus appears smaller, and travels more slowly across the face of the Sun, because it is much farther away from Earth. Transits of Venus are among the rarest of predictable astronomical phenomena. They occur in a pattern that generally repeats every 243 years, with pairs of transits 8 years apart separated by long gaps of 121.5 years and 105.5 years. The periodicity is a reflection of the fact that the orbital periods of Earth and Venus are close to 813 and 243-395 commensurabilities. The last transit to Venus was on 5 and 6 June 2012, and was the last Venus transit of the 21st century. The prior transit took place on June 8, 2004. The previous pair of transits were in December 1874 and December 1882. The next transits of Venus will be December 11, 2117, and December 8, 2125. Venus transits are historically of great scientific importance as they were used to gain the first realistic estimates of the size of the solar system. Observations of the 1639 transit, combined with the principle of parallax, provided an estimate of the distance between the Sun and the Earth that was more accurate than any other up to that time. The 2012 transit provided scientists with a number of other research opportunities, particularly in the refinement of techniques to be used in the search for exoplanets. Conjunctions. Venus, with an orbit inclined by 3.4 degree relative to the Earth's, usually appears to pass under the Sun at inferior conjunction. A transit occurs when Venus reaches conjunction with the Sun at or near one of its nodes the longitude where Venus passes through the Earth's orbital plane near and appears to pass directly across the Sun. Although the inclination between these two orbital planes is only 3.4 degree, Venus can be as far as 9.6 degree from the Sun when viewed from the Earth at inferior conjunction. Since the angular diameter of the Sun is about half a degree, Venus may appear to pass above or below the Sun by more than 18 solar diameters during an ordinary conjunction. Sequences of transits usually repeat every 243 years. After this period of time, Venus and Earth have returned to very nearly the same point in their respective orbits. During the Earth's 243 sidereal orbital periods, which total 88,757.3 days, Venus completes 395 sidereal orbital periods of 224.701 days each, equal to 88,756.9 Earth days. This period of time corresponds to 152 synodic periods of Venus. The pattern of 105.5, 8, 121.5 and 8 years is not the only pattern that is possible within the 243-year cycle, because of the slight mismatch between the times when the Earth and Venus arrive at the point of conjunction. Prior to 1518, the pattern of transits was 8, 113.5 and 121.5 years, and the 8 inter-transit gaps before the AD 546 transit were 121.5 years apart. The current pattern will continue until 2846, when it will be replaced by a pattern of 105.5, 129.5 and 8 years. Thus, the 243-year cycle is relatively stable, but the number of transits and their timing within the cycle will vary over time. Since the 243-395 Earth-Venus commensurability is only approximate, there are different sequences of the transits occurring 243 years apart, each extending for several thousand years, which are eventually replaced by other sequences. For instance, there is a series which ended in 541 BC, and the series which includes 2117 only started in AD 1631. History of observation. Ancient history Ancient Indian, Greek, Egyptian, Babylonian and Chinese observers knew of Venus and recorded the planet's motions. The early Greek astronomers called Venus by two names Hesperus the evening star and Phosphorus the morning star. Pythagoras is credited with realizing they were the same planet. There is no evidence that any of these cultures knew of the transits. Venus was important to ancient American civilizations, in particular for the Maya, who called it Noek, the Great Star, or Xuek, the Wasp Star. They embodied Venus in the form of the god Kikukaen. In the Dresden Codex, the Maya charted Venus' full cycle, but despite their precise knowledge of its course, there is no mention of a transit. However, it has been proposed that frescoes found at Meir Yapen may contain a pictorial representation of the 12th or 13th century transits. 1639 A first scientific observation equals. In 1627, Johannes Kepler became the first person to predict a transit to Venus, by predicting the 1631 event. His methods were not sufficiently accurate to predict that the transit would not be visible in most of Europe, and as a consequence, nobody was able to use his prediction to observe the phenomenon. The first recorded observation of a transit of Venus was made by Jeremiah Horrocks from his home at Carr House in Much Hall, near Preston in England, on December 4, 1639. His friend, William Crabtree, also observed this transit from Broughton, near Manchester. Kepler had predicted transits in 1631 and 1761 and a near miss in 1639. Horrocks corrected Kepler's calculation for the orbit of Venus, realized that transits of Venus would occur in pairs 8 years apart, and so predicted the transit of 1639. Although he was uncertain of the exact time, he calculated that the transit was to begin at approximately 1500. Horrocks focused the image of the Sun through a simple telescope onto a piece of paper, where the image could be safely observed. After observing for most of the day, he was lucky to see the transit as clouds obscuring the Sun cleared at about 15:15, just half an hour before sunset. Horrocks' observations allowed him to make a well-informed guess as to the size of Venus, as well as to make an estimate of the mean distance between the Earth and the Sun the astronomical unit. He estimated that distance to be 59.4 million miles about two-thirds of the actual distance of 93 million miles, but a more accurate figure than any suggested up to that time. The observations were not published until 1661, well after Horrocks' death. 1761 and 1769. In 1663 Scottish mathematician James Gregory had suggested in his Optica Promota that observations of a transit of the planet Mercury, at widely spaced points on the surface of the Earth, could be used to calculate the solar parallax and hence the astronomical unit using triangulation. Aware of this, a young Edmund Halley made observations of such a transit in 1676 from St Helena, but was disappointed to find that there had been only one other observation of the event and was not satisfied that the resulting calculation of the solar parallax at 45 inches was accurate. In a paper published in 1691, and a more refined one in 1716, he proposed that more accurate calculations could be made using measurements of a transit of Venus, although the next such event was not due until 1761. Halley died in 1742, but in 1761 numerous expeditions were made to various parts of the world so that precise observations of the transit could be made in order to make the calculations as described by Halley an early example of international scientific collaboration. This collaboration was, however, underpinned by competition, the British, for example, being spurred to action only after they heard of French plans from Joseph Nicolas de Lisle. In an attempt to observe the first transit of the pair, astronomers from Britain, Austria and France traveled to destinations around the world, including Siberia, Norway, Newfoundland and Madagascar. Most managed to observe at least part of the transit, but successful observations were made in particular by Jeremiah Dixon and Charles Mason at the Cape of Good Hope. Less successful, at St Helena, were Neville Maskelyne and Robert Waddington, although they put the voyage to good use by trialling the lunar distance method of finding longitude. The existence of an atmosphere on Venus was concluded by Mikhail Lomonosov on the basis of his observation of the transit of Venus of 1761 from the Imperial Academy of Sciences of St. Petersburg. He used a two-lens achromat refractor and a weak solar filter and reported seeing a bump or bulge of light off the solar disk as Venus began to exit the Sun. Lomonosov attributed that effect to refraction of solar rays through an atmosphere. He also reported the appearance of a sliver around the part of Venus that had just entered the Sun's disk during the initial phase of the transit. In 2012, Pasachoff and Sheehan reported, based on knowing what Venus's atmosphere would look like because of Pasachoff and Schneider's observations of the 2004 transit to Venus, that what Lomonosov reported was not Venus's atmosphere. To make a decisive test, a group of researchers carried out experimental reconstruction of Lomonosov's discovery of Venusian atmosphere with antique refractors during the transit of Venus on June 6, 2012. They observed the Lomonosov's arc, and other aureole effects due to Venus's atmosphere and concluded that Lomonosov's telescope was fully adequate to the task of detecting the arc of light around Venus off the Sun's disk during ingress or egress if proper experimental techniques as described by Lomonosov in his 1761 paper are employed. For the 1769 transit, scientists traveled to Canada, San Jose copyright Del Cabo, Tahiti, and Norway. The Czech astronomer Christian Mayer was invited by Catherine the Great to observe the transit in St. Petersburg with Anders Joe and Lexiel, while other members of Russian Academy of Sciences went to 8 other locations in the Russian Empire, under the general coordination of Stepan Rumovsky. The Hungarian astronomer Maximilian Hell and his assistant Jarno Sajnovics traveled to Vardar, Norway, delegated by Christian Seven of Denmark. William Wales and Joseph Diamond made their observation in Hudson Bay, Canada, for the Royal Society. In Philadelphia, the American Philosophical Society erected 3 temporary observatories and appointed a committee, of which David Rittenhouse was the head. The results of these observations were printed in the first volume of the Society's Transactions, published in 1771. Observations were also made from Tahiti by James Cook and Charles Green at a location still known as Point Venus. This occurred on the first voyage of James Cook, after which Cook explored New Zealand and Australia. This was one of 5 expeditions organised by the Royal Society and the astronomer Royal Neville Maskelyne. Jean-Baptiste Chappe d'Autereau went to San Jose copyright Del Cabo in what was then New Spain to observe the transit with 2 Spanish astronomers. For his trouble he died in an epidemic of yellow fever there shortly after completing his observations. Only 9 of 28 in the entire party returned home alive. The unfortunate Guillaume Le Gentil spent 8 years traveling in an attempt to observe either of the transits. His unsuccessful journey led to him losing his wife and possessions and being declared dead. Under the influence of the Royal Society, Rua Boakovia traveled to Istanbul, but arrived too late. Unfortunately, it was impossible to time the exact moment of the start and end of the transit because of the phenomenon known as the black drop effect. This effect was long thought to be due to Venus' thick atmosphere, and initially it was held to be the first real evidence that Venus had an atmosphere. However, recent studies demonstrate that it is an optical effect caused by the smearing of the image of Venus by turbulence in the Earth's atmosphere or imperfections in the viewing apparatus. In 1771, using the combined 1761 and 1769 transit data, the French astronomer Jar copyright Rami Lalande calculated the astronomical unit to have a value of 153 million kilometers. The precision was less than had been hoped for because of the black drop effect, but still a considerable improvement on Horrocks' calculations. Maximilian Hell published the results of his expedition in 1770, in Copenhagen. Based on the results of his own expedition, and of Wales and Cook, in 1772 he presented another calculation of the astronomical unit, 151.7 million kilometers. Lalande queried the accuracy and authenticity of the Hell expedition, but later he retreated in an article of Journal des Arts section Avens, in 1778. 1874 and 1882. Transit observations in 1874 and 1882 allowed this value to be refined further. 3 expeditions from Germany, the United Kingdom and the United States were sent to the Kerguelen archipelago for the 1874 observations. The American astronomer Simon Newcomb combined the data from the last 4 transits, and he arrived at a value of about 149.59 million kilometers. Modern techniques, such as the use of radio telemetry from space probes, and of radar measurements of the distances to planets and asteroids in the Solar System, have allowed a reasonably accurate value for the astronomical unit to be calculated to a precision of about a plus or minus 30 meters. As a result, the need for parallax calculations has been superseded. 2004 and 2012. A number of scientific organizations headed by the European Southern Observatory organized a network of amateur astronomers and students to measure Earth's distance from the Sun during the transit. The participants' observations allowed a calculation of the astronomical unit of 149,608,708 km, a plus or minus 11,835 km, which had only a 0.007% difference to the accepted value. There was a good deal of interest in the 2004 transit as scientists attempted to measure the pattern of light dimming as Venus blocked out some of the Sun's light, in order to refine techniques that they hope to use in searching for extrasolar planets. Current methods of looking for planets orbiting other stars only work for a few cases, planets that are very large, whose gravity is strong enough to wobble the star sufficiently for us to detect changes in proper motion or Doppler shift changes in radial velocity. Jupiter or Neptune-sized planets very close to their parent star whose transit causes changes in the luminosity of the star. Or planets which pass in front of background stars with the planet-parent star separation comparable to the Einstein ring and cause gravitational microlensing. Measuring light intensity during the course of a transit, as the planet blocks out some of the light, is potentially much more sensitive, and might be used to find smaller planets. However, extremely precise measurement is needed. For example, the transit of Venus causes the Sun's light to drop by a mere 0.001 magnitude, and the dimming produced by small extrasolar planets will be similarly tiny. The 2012 transit provided scientists numerous research opportunities as well, in particular in regard to the study of exoplanets. Research of the 2012 Venus transit includes measuring dips in a star's brightness caused by a known planet transiting the Sun will help astronomers find exoplanets. Unlike the 2004 Venus transit, the 2012 transit occurred during an active phase of the 11-year activity cycle of the Sun, and it is likely to give astronomers practice in picking up a planet signal around a spotty variable star. Measurements made of the apparent diameter of Venus during the transit, and comparison with its known diameter, will give scientists an idea of how to estimate exoplanet sizes. Observation made of the atmosphere of Venus simultaneously from Earth-based telescopes and from the Venus Express gives scientists a better opportunity to understand the intermediate level of Venus atmosphere than is possible from either viewpoint alone. This will provide new information about the climate of the planet. Spectrographic data taken of the well-known atmosphere of Venus will be compared to studies of exoplanets whose atmospheres are thus far unknown. The Hubble Space Telescope, which cannot be pointed directly at the Sun, used the Moon as a mirror to study the light that had passed through the atmosphere of Venus in order to determine its composition. This will help to show whether a similar technique could be used to study exoplanets. Past and future transits. For a complete list see NASA's 6 Millennium Catalogue of Venus Transits, 2000 BCE to 4000 CE. Currently, transits occur only in June or December and the occurrence of these events slowly drifts, becoming later in the year by about 2 days every 243-year cycle. Transits usually occur in pairs, on nearly the same date 8 years apart. This is because the length of 8 Earth years is almost the same as 13 years on Venus, so every 8 years the planets are in roughly the same relative positions. This approximate conjunction usually results in a pair of transits, but it is not precise enough to produce a triplet, since Venus arrives 22 hours earlier each time. The last transit not to be part of a pair was in 1396. The next will be in 3089. In 2854, although Venus will just miss the Sun as seen from the Earth's equator, a partial transit will be visible from some parts of the southern hemisphere. Over longer periods of time, new series of transits will start and old series will end. Unlike the Saros series for lunar eclipses, it is possible for a transit series to restart after a hiatus. The transit series also vary much more in length than the Saros series. Grazing and simultaneous transits. Sometimes Venus only grazes the Sun during a transit. In this case it is possible that in some areas of the Earth a full transit can be seen while in other regions there is only a partial transit. The last transit of this type was on December 6, 1631, and the next such transit will occur on December 13, 2611. It is also possible that a transit of Venus can be seen in some parts of the world as a partial transit, while in others Venus misses the Sun. Such a transit last occurred on November 19, 541 BC, and the next transit of this type will occur on December 14, 2854. These effects occurred due to parallax, since the size of the Earth affords different points of view with slightly different lines of sight to Venus and the Sun. It can be demonstrated by closing an eye and holding a finger in front of a smaller, more distant object. When you open the other eye and close the first, the finger will no longer be in front of the object. The simultaneous occurrence of a transit of Mercury and a transit of Venus does occur, but extremely infrequently. Such an event last occurred on September 22, 373, 173 BC and will next occur on July 26, 69, 163, and again on March 29, 224, 508. The simultaneous occurrence of a solar eclipse and a transit of Venus is currently possible, but very rare. The next solar eclipse occurring during a transit of Venus will be on April 5, 232. The last time a solar eclipse occurred during a transit of Venus was on November 1, 607 BC. It could be noticed that the day after the Venerian transit of June 3, 1769 there was a total solar eclipse, which was visible in Northern America, Europe and Northern Asia. See also: astronomical transit, transit of Mercury, black drop effect, solar eclipse. Notes. Further reading: Hufbauer, Ph.D., Dr. Cal. Exploring the Sun, Solar Science since Galileo. Baltimore, The Johns Hopkins University Press, pages 29-30. ISBN 0-8018-4098-8. Anderson, Mark. The Day the World Discovered the Sun, An Extraordinary Story of Scientific Adventure and the Race to Track the Transit of Venus. Boston, Da Capo Press. ISBN 978-0-306-82038-0. Chauvin, Michael. Hokuloa, The British 1874 Transit to Venus Expedition to Hawaii. Honolulu, Bishop Museum Press. ISBN 1-58178-023-0. Lom, Nick. Transit of Venus, 1631 to the present. Sydney, Australia, New South Publishing. ISBN 978-74223-269-0. OCLC 717231977. Moore, Eli. Venus in Transit. Princeton, Princeton University Press. ISBN 0-691-11589-3. Maunder, Michael. Moore, Patrick. Transit, When Planets Cross the Sun. London, Springer Verlag. ISBN 1-85233-621-8. Sellers, David. The Transit of Venus, The Quest to Find the True Distance of the Sun. Leeds, UK, Magavelda Press. ISBN 0-9541013-0-8. Sheehan, William. Westfall, John. The Transits of Venus. Amherst, New York, Prometheus Books. ISBN 1-59102-175-8. Simon, Arkan. The Transit of Venus Across the Sun. Physics Education 39, 247 €251. Bibcode 2004 Fired 39 47 Estoy, 10.1088390001. Wolf, Andrea. Chasing Venus, The Race to Measure the Heavens. New York, Knopf. ISBN 978-0-307-70017-9. External links. General, Transit of Venus. Information, Venus transits, measuring the Solar System, historical observations of the transit of Venus, Edmund Halley's 1716 paper describing how transits could be used to measure the Sun's distance, translated from Latin. Chasing Venus, Observing the Transits of Venus, 1631 2004, Merrifield, Michael. Venus Transit. 60 Symbols. Brady Heron for the University of Nottingham. June 2012 Transit, 2012 Transit of Venus. International Astronomical Union, National Solar Observatory. Transit of Venus 5. June 6, 2012. 2012 Transit of Venus. Live Week cast and chat room with SEMS at UND. Live from Alaska.